and spend a few minutes sort of redefining what these enols and enolates are. I think most people looking at homeworks and thinking about office hour visits and what have you, they're okay with 20, they're getting used to 21. They're starting to see the differences in the chemistry in terms of things adding and things leaving, and the difference between a ketone and an acyl halide, stuff like that. What we're going to do now, and I'm going to be very careful with this, we're going to mix everything up. You're going to start throwing ketones in with esters and esters in with ketones. And that can get very, very confusing. What I will do before this next test is try to keep that as simple as I can and then mix it all up after the exam. There are some reactions coming up that I think are spectacular. The Robinson annulation process, conjugate addition followed by intramolecular aldol reaction, that is a beautiful reaction. I will leave that until after the exam. And when we get there, we'll start doing biosynthesis. We'll start putting molecules together. For those of you who have to take biochemistry, which is most of you at some stages in your lives, we'll start seeing how biology puts these molecules in place. So I'm starting off again at the beginning here just to make sure we're up to speed. And this idea of using an aldehyde or a ketone as a nucleophile. We have done lots of chemistry so far in which aldehydes and ketones have been electrophiles. We have attacked them with nucleophiles, be they Wittig reagents, be they Grignards, be they hydrides, stuff like that. You should be okay with that stuff. And that reversibility process is dependent upon what the nucleophile was. If the nucleophile also constitutes a good leaving group, it can break back off and you can make the decision to make it reversible. Well, when we get down to the enols here, we're going to talk about the acidity of these protons on the alpha position. We're going to talk about what type of bases you need to be able to take them off, and then how you can manipulate this to work out what's going to be in the solution at any one time. We'll say a weak base will give you an equilibrium, a strong base won't give you an equilibrium, and then you have to decide what you're going to add next in terms of doing alkylation type chemistry. So thinking about what an enol is a neutral species. It's something that has a double bond and it has an OH directly attached. That's an enol. And it's in tautomerism, or it's in equilibrium with the keto form. And you can see now that really what this is an isomerism. The two molecules have the same molecular formula, they have the same bits and pieces, other than the way they are arranged. We can see here the ketone has the double bond between the C and the O, the enol has the double bond between the C and the C. And this proton, which is highlighted in red, seems to be moving from the carbon at the alpha position to the hydroxyl to give you that OH group. Now, it's a bit more complicated than that. It is a stepwise process. It isn't an intramolecular process either. But it's nothing more complicated than what we've done. And I think what we tried to do in the recitation this week, which people said was quite useful, was organize stuff and talk about what happens in acid and what happens in base. And you'll see this again today. If you understand protons and positive things and you understand bases and negative things, this is no more difficult than anything we've seen. So we get tautomerism. We get this process in which the ketone goes to the enol goes back to the ketone. And you'll need to be careful because that's often disguised in a reaction. You'll often have the product as a ketone, but you ended up with the enol and you forgot to enolize. That will be an issue in the near future. Enolates are different in the sense that they are now negative species. In fact, they are the conjugate bases of the enol, if you take off one of those protons. And we could again draw two pictures for this. We've got to be very careful here. We're drawing at the top equilibrium because these are two distinct species. If you had these two in a mixture, you would see the OH group in the infrared spectrum. You would see the carbonyl in the infrared spectrum because they are different molecules. But down here, this idea of delocalization with the enolate, no, they're not different. They are the same molecule, and this is the best we can do to sort of draw where the charge will be. So what we'll try and do today is redefine these things and talk about their relative stabilities, and then get into some of their chemistry and how you make them. So in terms of geography, we've got to be happy with these molecules in the idea of where things are. The carbonyl itself doesn't get a designation. That's sort of the middle of it. Next door to that is the alpha position. So this alpha position here, if the molecule is not symmetrical, you can have two alpha positions. You really can't have more than that for a ketone. And with an aldehyde, how many alpha positions can you have? Just the one, right? Because one side is a hydrogen. And I'll make a comment about that in a second. We can look at molecules like this at the bottom. On the left, you have a methyl group, which has 3 hydrogens. You'll take off one of them sequentially. You might take off 2 eventually, or 3 eventually, but only one comes off at any one time. And with molecules like this, we have to be careful because the right-hand side does not have an alpha proton. For those of you who like to draw hydrogens randomly and make 6 bonds to carbon, this can be a lot of fun. But for those people who pick this up and doing it properly, there are no protons on the alpha position on the right. Now, this molecule here, I'm going to say this a number of times, that proton there is never, ever, 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 ever acidic. So don't take it off. Make a note of that, please. You'll make me a very happy man if you don't take that proton off. Because there are plenty of other protons to take off. And the ones that will come off are at the alpha position. And why are they special? Because they're right next to the carbonyl, and they can delocalize into the carbonyl if you do take that off and make a negative charge. So be careful with aldehydes. We'll see that as we work our way through the chapter. Well, we can go from ketones or aldehydes, and we can treat them with acid or base, and we can do alkylation chemistry, specifically at the alpha position. So this now is saying that this position is activated. This position is special. Again, it's because of the fact that the carbonyl is an electron withdrawing group. It's pulling electrons away from its neighbors, which makes them maybe a little bit more acidic. But also, when you take that charge, when you take that proton off and you make it negative, you've got delocalization possible. So what we will see coming up very soon, very quickly here, is if you take a strong base, you can deprotonate and make the enolate. And again, that enolate is somewhere between the charge on the O and the charge on the C. Now, where would you rather have the charge? On the oxygen or on the carbon? On the oxygen. So we might say that the enolate structure is more important. The molecule looks more like the enolate. And at the top, if we use acid or base, and this will happen also at neutral pH, you can produce the enol in tautomerism with the starting ketone. We'll see that that's absolutely essential in some of the reactions that we're about to study. If you don't have that enol in there, the chemistry is impossible. So we'll keep an eye on the fact that this thing is definitely in there. We just have to remember that. Now, at the end of this, what we need to worry about is alkylation chemistry or attack on some electrophile. So we should be okay now from the past with the idea that a double bond is going to go after something positive. All the way from from chapter 5 and 6, way back when. We go after protons, we go after bromine, things like that. And we'll end up with an alpha functionalized ketone. Now, having said that, I mean, that's a very simple thing to say, but you will see through the rest of chapter 22 that that's a huge amount of chemistry. And it's a huge amount of biochemistry too. So we can now think about the differences between an enol and an enolate. Which do you think is more reactive, the enol or the enolate? Enolate, right, because it's basic and it's like hydroxide, it's going to go after things. But we'll see both of them in different circumstances depending upon what the pH happens to be. Now at the bottom we can see again, if we pick up the electrophile, we can do something like that. And again, Markovnikov addition applies. You want to go through the best intermediates you can. And the same rules apply about charges. If you have an acid reaction, you're looking at positive things. If you have a basic reaction, you're looking at negative things. Pretty much every ketone will have an enol, but there might be not much of it, there might be a lot of it, depending upon the overall structure. And so now, in terms of the sort of prevalence of these things in a solution, if you were to take a sample of this cyclohexanone, and you were to take its NMR spectrum, and you took maybe the C13 spectrum, you would see that carbonyl signal down at 200 ppm. And you wouldn't see much of anything for this. In fact, when we're getting down to this sort of percentage, we're talking about the limits of the instrument. What can the instrument measure? So you're not going to see very much of this stuff at all. If you took the infrared spectrum of this stuff, you'd just see the carbonyl at 1750. You probably wouldn't see much of the OH group because of that difference in proportion. And all that's saying now is that this ketone, in that simple example, is more stable. Any equilibrium tends to favor the more stable material. So if we're saying now that in the spectroscopy you just see the ketone, that tells you the ketone's more stable. You measure the bond energies, it is. So ketones tend to be favored, unless there are some different circumstances that allow the enol to win. So these two examples show that you can have enols that are significant in terms of their proportion in a mixture. And at the top we have something that you'll see after the exam when we talk about 1,3-dicarbonyl compounds. Only 10 to 30% of this stuff happens to be the keto form, and the rest of it happens to be the enol form. And we mentioned on Wednesday that this has got some, there are some extenuating circumstances here that didn't happen in the previous example. There's no hydrogen bonding possibilities in that previous example, but having that second carbonyl here allows for this intramolecular hydrogen bond, and that's glue that holds the molecule together, so that's good. That makes it stable. But we also have this idea of conjugation, and we'll see a lot more of conjugation after the test when we start talking about addition to conjugated compounds that contain ketones. So again, this is not the normal situation for a ketone. You have to have some features in there that make it special, and in this case the second carbonyl does. And I think everybody was okay with this idea. This is the keto form, and very little of it exists, and it's mostly that. And the answer is because you want that aromatic cycle. That is incredibly stable, or quite stable, so you want to get there. It's desirable. So trying to prove again that some of these basic ideas, I'll not use that word, some of these central ideas are important. This idea of keeping a track of mechanisms and organizing yourselves. These are two mechanisms to get from a ketone to an enol. And the only difference now is the pH. In one at the top you have acid, so you're at low pH, everything will be positive. At the bottom, basic, because you're throwing in hydroxide, everything will be negative, and therefore a different mechanism. But you get to the same place. You start out on the left with a ketone, and you end up on the right with the enol. So how do we get there? Well, if you have an acid, guess what you do first? Productive. So now we'll protonate. That's absolutely right, proton transfer. Again, if you go back into the earlier chapters of the book when we introduced mechanism, the author says that there are basically 4 types of arrows. Proton transfer, nucleophilic attack, leaving group breaking off, rearrangement. And you follow these mechanisms, that's all that's happening. There's nothing extra here. So you protonate, and what's the whole point of this? And in this example, he does draw my second resonance structure. This is good, right? We kind of skipped some of those structures from the earlier figures from the book, but I want those structures in there. What is this showing you? Why am I wanting this resonance structure? Show it's more reactive, absolutely. To show that this species is now more reactive. And you've got to keep in mind this catalysis idea. We're not finished with catalysis by a long way. And biochemistry is what, 95% catalysis. You've got to be happy with this stuff. The idea now that you protonated the oxygen's not happy. It wants that lone pair back. And we can show that with this second resonance structure in which it really looks like a resonance stabilized carbocation. And any carbocation needs help, and it needs to be able to pick up some electrons from some place. To get to the enol form, and we'll confuse this next week and the week after by saying that you can go in many different directions here, but ultimately you end up in the best place. What does this reaction remind you of, that second step of that process? What does that look like? What mechanism does it remind you of? E1, absolutely, good, E1. And that gives you this guy at the right-hand side, gives you the enol form. That's how you get there. Now, we don't make enols just for their own sake. We're going to make them to do something with. We're setting this up. And when we get to enolates in a minute, we'll do the same thing. We'll set them up. We'll show you how to make them, and then consider, what do I want to happen next? Do I want the enol to attack the ketone, or do I want the enolate to attack something else? And we can do that very carefully if we set up the experiment properly. Now at the bottom, and let's just wrap that up by saying, okay, positive species, positive species, positive. All right, everything was positive on that reaction profile. Now at the bottom, we have changed the pH. We've made the pH a lot higher. You've put in hydroxide, and I hope we're happy now with the idea that if you purposely put hydroxide into your flask, you are allowing negative things to live. You're allowing bases to be okay. You're allowing leaving groups to break off that in the past didn't break off, because you have set this experiment up to make the system negative. You make it very basic. So what's happening now, and somebody asked this question on Wednesday, and I'll repeat the answer. Can it attack the carbonyl? Yes, it can. But it can break back off, because you're at high pH, and that hydroxide is a leaving group. So in this mixture, you might get some of the hydrate, but you'll also get some of the enol. The hydrate is dead. It doesn't really go anywhere apart from back to the ketone, but the enol can go other places and end up with a stable product. So if we take the hydroxide, this is probably the first example of taking off that alpha proton with a base. The deprotonation alpha to the carbonyl to set up the enolate. Now, the only reason this happens at the alpha position is the fact that it can delocalize into the carbonyl. If you're at the beta position, it's too far away, gamma, way too far away. So it only happens at the alpha position. And these two resonance structures are something that you should be very, very happy with and comfortable with. The idea that we have something that looks like a carbanion and something that looks like an alkoxide, somewhere in between. And in this class, I'll say this when we get there again, but in this class, all the chemistry will happen at the alpha position. All the chemistry is going to happen at the alpha carbon. Later classes, maybe you'll get some oxygen chemistry. Take intermediate organic with Dr. Jackson, maybe you'll put something on oxygen. But everything we're going to do here involves the alpha carbon. So this picture here is very important. This will serve as the nucleophile where the charge is developing on the carbon. And to get to the enol, to finish this off, I simply have to do a proton transfer to the oxygen, and that gives me the enol. So those two mechanisms, I would hope at this stage, don't require much thought. They don't require much studying because they do look an awful lot like things that you've seen. And as I've seen a lot of people doing this week in office hours, which I think is good, there's the starter material, there's the product, in quotes, because it's going to go someplace else in a minute. You first of all need to know where it goes, and then that will help you work out the mechanism. So write a flashcard or a study sheet, whatever you call them, with the product in there so that you know that, and then you can help yourself work out the mechanism. Here is a picture that shows the electronic characteristic of the enolate. My bad, sorry about that. The enol. This thing is neutral. And what's happened here is that the model up here, which is trying to show, the hot component here and the cold component in terms of electron density, the oxygen's obviously hot because it's got two lone pairs. But it turns out now that the carbon down here is starting to get warm because it's got some electron density. And where that comes from is simply the enolate form. So I can pick this thing, I can push these electrons over here and draw this second resonance structure for the enol, in which we can draw a negative charge on the alpha carbon. Now, in reality, what that means is that this carbon right here is delta negative. That carbon right there is nucleophilic, it's delta negative, just because of the fact that the oxygen's pushing electrons in. We have seen this before. Where have we seen that before? Hydroxyl next to a pi system, pushing electrons in. Where was that? Anybody? Say again? Not the Wolff-Kishner necessarily. A couple of chapters ago. Benzene chemistry, good, benzene chemistry, right? Hydroxyl pushing electrons in, it's doing the same thing here. Pushing the electrons in, making things more nucleophilic. It's the identical idea. So, to go from an enolate, or an enol to an enolate, you have to take off one of those protons. And this discussion now really cements, I think, whether you understand pH or not, and whether you understand what equilibrium is trying to do. So I have at the top, you know, the simplest ketone we can look at really is acetone, and we'll use it as a model. And think about what happens with a base. Now, a base can be a nucleophile, it can go after the carbonyl, but it can also break back off usually. And we'll use some bases that don't attack the carbonyl. We'll design some bases that stop attacking at the carbonyl and they only go for the alpha position. So if you take a base and you go after the alpha proton, you can produce the enolate, which we've said already is resonance stabilized. And we just argued that probably it looks more like this because more of the charge is on the O, which is better. But if you had to draw some sort of resonance hybrid for that, we'd probably have something like this in which the O and the C are sharing the charge, and we have a dotted line to show that. And I would put delta negative on here, and I would put delta negative on here. And all of a sudden, we've got a nucleophile, which is nucleophilic at several different places, or at least 2 different places. That can go after the electrophile and attack, and you get what we call either O alkylation or C alkylation. On the left, O alkylation is very rare, especially at this level. So you're not worrying about that too much, but that is possible. All the reactions that we study, we get the other thing over here, and we get C alkylation. And the answer why is because you want the carbonyl back. The carbonyl is quite stable. We just proved that with the enols and the ketones. Typically, it's the ketone that's favored, so you want it back. So in this example on the right, you'll see a lot of this. In fact, most of this chapter is doing this, attacking carbonyls. It just depends upon what the electrophile is, and you end up with a functionalized product. Now, in terms of what enolates do, there are the arrows that you can draw. I don't mind which one you use. Some people like enolates or like the enolate picture. Some people like the carbanion picture. They are identical because really they are the same molecule, aren't they? They are related like that. And so those 2 pictures are identical, whichever you prefer. So the point is that these 2 sets of arrows are the same. I don't mind which one you use. This one takes less ink. That's the only difference. But they are identical in terms of what you do. And they are identical in terms of the outcome. So the point is you will be drawing fairly soon resonance structures for enolates and then going after something. And it doesn't matter which picture you use to go after. I myself usually use this one, but it doesn't matter. Okay. Now, in terms of doing this, we've got to be very careful where we take protons from. This is just an aldehyde again. This is the butyraldehyde. And it's more a sort of let's hammer this now and get it in your heads. This proton never comes off. It should never come off. And why should it not come off? Because if I do take that off, where does the negative charge go? Onto this carbon right here. Now, some people might think, well, can't you do resonance there? And the answer is no, because you've got the negative charge on the same carbon of the pi bond. And in fact, if you think about the orbitals here, and you put a negative charge on this carbonyl, what direction is it in compared to the pi bond? Think about where the orbital has to be. The pi bond's up and down. Where's the negative charge? It's pointing out at the side at 90 degrees. It's got no help whatsoever from the carbonyl. So you can't do deprotonations here. It's actually a very classic old problem in organic synthesis. You have to do some very elegant workarounds to make this work. But that proton, as far as you are concerned, will never, ever, 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 ever come off. Over here, yes. And it depends now upon how many you have. If you don't have any alpha protons, you can't deprotonate it. If you have 1, you can make an enolate. If you have 2, you can do some very elegant reactions coming up in which you sequentially deprotonate. Deprotonate, do something, deprotonate, do something. Or if you have 3 of them, deprotonate, do something, deprotonate, do something, deprotonate, do something. Right? So the bromoform reaction involves that. So keep an eye on this. Just make sure you understand why it's only the alpha position that's activated, and make sure that we're only taking those protons off. Now, obviously, this is different. The molecules are getting bigger. If you've been sensible about this, you've got 20 and 21 worked out already, and you're just starting to think about this now. And you've got a week to get this into your heads. You're looking at more complex molecules, no doubt. But if you do take biochemistry, and, you know, Gina was saying that the average on the biochem test this week was, what, 42? Which is actually quite good for a biochem test. It's because things get bigger and more confusing and more complicated. But we're taking it slowly in steps to get there. So you look at this molecule at the top. It's obviously a ketone. It's a more complicated ketone. It's starting to look like a terpene. It's starting to look like a natural product that might have some use in medicine. And we're trying to use that as a starting material. That's our precursor that we are able to get hold of in large amounts, and we want to do some chemistry with it. Now, when you think about this system, you have several choices. You think about carbonyls, you can attack those. You've seen that a lot with hydride, Grignard, Wittig reagents, stuff like that. That works very nicely. But now we're saying, what's the consequence of this molecule in the presence of a base? What happens? And we've got to identify alpha carbons, which is exactly what's happened here with the green lozenges. Now, in that molecule, very careful, don't be putting hydrogens where hydrogen shouldn't be. These two alkyl groups kill that alpha position. There is not an acidic proton at that alpha position, so you cannot take it off. As opposed to on the left, yes, that can definitely come off. And we'll see an argument fairly soon in which we talk about double bond structure again. And more highly substituted double bonds are preferred over lesser substituted double bonds. Same idea from Zaitsev. But in this case, it's fairly straightforward because you've only got one proton to take off, and because it's trapped in a cycle, you're not going to get the possibility of cis-trans isomerism or anything like that. So if the base comes in, and I haven't told you what the base is yet, but I will soon, we come in, take that proton off, and we put the charge here. Now again, the questions will always say, draw all the resonance structures to describe the intermediate. And that means we have to be comfortable with these pictures down here. This is a more complicated structure. We just went from acetone, which is about as simple as it gets, to something that's biological very quickly. But it's the same idea. You've just got to transfer what you know from the simple system into the more complex system. And it usually works quite well. So with that in mind, we can start to talk about bases. I would say that this concept, you think about what you learned in high school, what you learned in freshman chemistry, and what you're learning here. Acids and bases are about as most useful as it gets. Now, they're probably one of the least understood processes. And when you get into biochem, acids and bases, the idea of a peptide, the idea of a protein and its structure in terms of isoelectronic points, acids and bases. So the fact here on this slide is the first definition of what is the acidity constant for that type of system. It is the first discussion of an actual pKa for that system. And it turns out here we have an aldehyde. Aldehydes are quite acidic. If you think about water, pKa of about 16, this is in the same region. And you think about biosynthesis and the idea of using these as structures to do biosynthesis, then that pKa is important. To be able to lower that pKa is important. Why is it 16 and not 50 or 60? Because the carbonyl's there. So how much influence does that carbonyl have on this? A huge amount. Don't forget that system is logarithmic. And so going from 50 down to 16 is a huge leap. We can take this proton off using a base such as ethoxide. And we have to go all the way back to the first chapter, but we've been doing this since, and worry about this system here. Worry about the idea of equilibrium. Where does the equilibrium lie? If I use a certain base, am I going to go all the way to the right? If I use a different base, do I get any deprotonation or do I get an equilibrium? That will be absolutely essential now. So if I do this and take this proton off at the alpha position, I get my enolate. And I can draw obviously a second resonance structure that describes why that is stabilized. But for this particular slide, it's the formation of this that's important. And the pK of that is pretty much 16. Okay? So going back all the way to the acid-base stuff, we've got to worry about which side is favored. And in fact, on the left, you have the weaker acid by a little bit. And on the right, you have the stronger acid by a little bit. So the left-hand side is favored. What is K for that process? What is the equilibrium constant? Less than 1, greater than 1, or approximately 1? Less than 1. It is less than 1, right? Left-hand side is favored by a little bit. What does that mean? It means, and this is important now, at any time after you put that base in that mixture, you have some of the aldehyde and some of the enolate at the same time. You have one in the presence of the other. That will be important because one will be an electrophile, E+, and the other piece will be a nucleophile. And they will go after each other. So if you set this up so that you have both in there, they will attack each other. And you'll get a complex reaction we'll call the aldol reaction a little bit later, and that enables us to knit carbons together and do carbon-carbon bond-forming reactions. Well, that's one set situation in which a strongish base deprotonates a decent acid or a weakish acid and gives you the material on the right. Now, what if you want this to go completely? What if you want to take this proton off and not give it back? What do you have to do to the base? Make it stronger or weaker? Make it stronger. Make it very strong. And we have some very good strong bases. We'll see some new ones now that are designed for this type of chemistry. But something as simple as hydride, NaH. You've seen that before. NaH will do this quite nicely. In this example, we have, again, the pK here is about 16.7. And if you deprotonate with hydride, you're not going to get the hydrogen gas back because it went away. It bubbled away. You run these reactions, you see bubbles. And that's the hydrogen gas disappearing, and it's out of the equilibrium, so you're not able to go backwards. So the conjugate acid of the base is gone. And that means the right-hand side is completely favored. Now that makes a big difference. If the right-hand side is completely favored, it means there is none of this left. There is none of the aldehyde left. So you can't attack the aldehyde because it's gone. It all became enolate. So what you tend to do with these types of reactions is then, once the enolate is formed, you add something else. You add some electrophile that can then be attacked. That's very versatile because you can pick and choose the electrophiles. But the key on this slide, and this is I think probably the most important slide today, is that the choice of base will determine the outcome in terms of whether you have an equilibrium or not. Choose a base with approximately the same pKa in its conjugate acid as what you start with, you'll get an equilibrium. Choose a base that has a very different, I think the pKa of H2 is about 45, and that doesn't really matter because the hydrogen's already bubbled away, so it's not coming back anyway. That favors the right-hand side, which means all this. If you get that, that sets up what happens next when we actually put this into practice and we start doing some reactions. So very powerful base, all the right-hand side. Weakish base, bit of both. Other systems, but in this example on this slide, you can see acetone right there. The pKa of that ketone is 19.2. It's not as acidic as the aldehyde. And we might be able to work that one out. If we have an H here with a double bond and a methyl group, the pKa of that is about 17. But the pKa of a ketone is 100 times higher. Any ideas? What's the difference? If you take off this proton here and you put a negative charge there, what effect will this methyl group have on the left-hand side? Electron donating. Wow, well played. This is electron donating. So you've got electrons trying to go in from both sides of that carbonyl. That will destabilize that enolate compared to the aldehyde, in which you don't, because the hydrogen over here isn't donating very much. So a very simple idea. It's also, related to the reactivity of aldehydes and ketones that we developed earlier. If you have that second alkyl group, it will destabilize the enolate, which means the acid won't be as strong. But it's still deprotonatable. You can still take this thing off. You can take off with 19, you can take off with simple things like hydroxide or ethoxide, and we'll see some designer bases in a second that allow that to go completely to product. Acetophenone, 18.3, somewhere in between. Maybe that benzene ring is helping share some of the electron density a little bit. And again, you see the enolate on the right, and then down there, acetaldehyde, which is the strongest of the lot, and that's because of the fact that there isn't a second donating group. If that was a typo right there, isn't there? That should be an H if you have this in front of you. So very subtle things that will play a large role in the type of base that you have to choose. Now, I mentioned designer bases. This is a very, very useful base. This is a very powerful base. It is a nitrogen base called lithium diisopropyl amide. And everybody in the audience ought to be able to tell me what the approximate pKa is for that NH bond. 38, quite high. So that tells you you need to take it off with a quite powerful base. Now this might be counterintuitive. We're going to use a very powerful base to take off a proton to make a very powerful base. But obviously everything we do here is sensible, so there is a reason behind that. It turns out that this particular base, N-butyl lithium, and compounds like it, like Grignard reagents, attack carbonyls. And we don't want that. Those types of little Grignards, little alkyl lithiums, are quite nucleophilic. And because it's a long chain, it can get places. It's not that crowded. So we can use that if we want to add to a ketone. We'd go after the carbonyl. That's fine. We can make carbon-carbon bonds doing that. But we don't want to do that here. We want to have a base that only deprotonates at the alpha position, so we get selectivity. So the whole point of these sort of deer antlers right here, the isopropyl groups, is to make it large. And that thing is big and bulky, and it tends not to attack carbonyls. So the whole point of using a strong base to deprotonate an acid to give you a strong base is the size of these things. Okay? These things are going to stop any addition at the carbonyl. So instead what we get is attack at the alpha position. We get deprotonation. Again, the byproduct here is butane, disappears, and that's an irreversible reaction. It's a very useful way of doing this. Now, when you run this reaction, any idea about temperature? What sort of temperatures would you do this at? Would you want to boil this thing? Would you want to do it low temperature? What are we thinking? You've got an exothermic reaction. It's exothermic by quite a bit. Do you want to cool this down or warm it up? Cool it down to avoid any problems. And we typically run these things. You'll see these details on old exams and in the book, this is typically done at sort of negative 78 degrees C. Why so specific? Well, it turns out, some of you might have done this already, if you take acetone in the lab and you put it in a bowl, and then you add some dry ice, the acetone dry ice mixture gets down to negative 78. It's very simple to do, it's very useful. So it's not arbitrary at all, it's just the fact that practically it's the easiest thing we've got. Dry ice and acetone gives you that temperature. And we want to keep things cool to stop things degrading and falling apart, and also to avoid exotherms. If this is a highly exothermic reaction, you don't want things getting hot and out of control, so you keep it cold. So what it allows you to do is selective deprotonation at the alpha position, with no nucleophilic attack on the carbonyl. The butyl lithium at the top would go after the carbonyl, and you get a Grignard type outcome. We don't want that. So we have a super powerful base, and we have a reasonably acidic proton. And if we do this reaction, we make the enolate just as we've done before with the generic B for base, and ultimately we get this guy at the right-hand side. And its pK is in the 36-38 region. So is that reaction going backwards? No. No, that's not acidic enough. So this is the basic idea of getting this thing to work. Use the big base, take off that proton, it's not going to give it back. We now have a flask which is full of enolate. And there's nothing better than that. Because then you can alkylate things, you can add other things to them. Moving on, weak base, equilibrium. Strong base, right-hand side completely favored. That is the take-home from today. You can also enhance the acidity of the carbonyl system. This is, we talk about it now because that's the flow of the book and the way they introduce it, just keep it all together, but this will come after the test. If you put a second carbonyl in here, you would expect the pKa to go lower, because those two carbonyls now work in tandem to pull electron density away from the middle of the molecule, and I've got electrons being pulled in this direction, electrons being pulled in that direction, so this proton down here should be easier to take off. It should be a little bit more acidic. And in fact, now the pKa is 9. And when we said way back that carbon molecules have pKa's in the 50s, obviously it's got very different now. Right? 9 is very, very acidic. There are carbon acids out there that have negative pKa's. Just depends what you put on them to make it so. In this example, between the two carbonyls, this 1,3-diketone system, ethoxide now is plenty strong enough to completely deprotonate this thing. So it's worth going back and looking at pKa's again. On the left-hand side, I have 9. On the right-hand side, I have 16. That's a 7-unit difference. 10 to the 7 is a lot. So the right-hand side is pretty much completely favored. So you don't need to use the nuclear option here. You don't need the LDA here because this will work. This will give you complete deprotonation. And the answer again is resonance structures. We should be okay now with these things without memorizing them. We can delocalize left, we can delocalize right, and we end up with 3 different resonance structures to explain the stability of that thing. And some of these things you can isolate as salts. Right? We're getting to the point where these things are stable enough. Lots of things happen here. You can deprotonate in different places. You've actually got 2 places to deprotonate. Why not deprotonate here? They're alpha protons. Why not take off there? Because they're less acidic, because they don't have 2 carbonyls involved. But later on, you might be able to take it off with a different base or another base. Yeah, you've got to be careful. Nucleophilic addition does happen with those small bases, but it's reversible and comes back off. And think about this now. If it comes back off and allows this to happen, this is irreversible. So it's driving. You know, you get stuck in some place, you reverse and try and get back out and try and get where you're going. This is going backwards and forwards and eventually finds its way here, and this is irreversible. So you're like that. That's what you do. A lot of that to come. It's good stuff. So we're just showing you some examples now of systems that you can enhance, in which you can enhance the acidity by changing the structures subtly. But overall, there's the take-home. We'll be able to talk about designing these things and then picking the appropriate base for esters. So this slide sort of summarizes what I just said. If you have a ketone, which is a single ketone, a monoketone, and you choose a small base, you will get deprotonation. You will get attack at the carbonyl. You will get a mixture of things. But it turns out now that both of these things, this and the starter material, are left in the solution, which is really important because they can go after each other later. At the bottom down here, if you choose a very powerful base or one that won't give its proton back, you go completely to enolate. There is none of this left. 100% enolate. So it can't attack anything else unless you put something else in. That's a bunch of reactions to come. Right, on the right-hand side, you don't need to use the nuclear option because that proton in the middle is acidic enough. You can use something like hydroxide or ethoxide or methoxide, and you take that proton off and it doesn't come back because the pKa difference is so large. So what we've done so far today is we've gotten this idea that yes, alpha protons are acidic, and how to take them off and the extent that you take them off. So do you want them all? Do you want all of them taking off? Use a strong base. Do you want some of them taking off? Use a weak base. Because that then sets up the chemical reactions that will happen next. Well, these types of reactions are useful to us to produce what we call alpha bromoketones. We've got the alpha position here with a bromine attached. That's alpha bromo cyclohexanone. And how this works, I think, really tests whether people understand what's happening here. Because all the way through these almost 2 semesters now, much of what we've done has been identify a nucleophile, identify an electrophile, and let them go after each other. And we end up with some bonds and we end up with some products. But we're now trying to functionalize this carbon here, which doesn't have anything there to functionalize. I don't see any lone pairs. It's not negative. I don't see anything there. It's not electrophilic, right? There's no sort of delta positive stuff happening there. So how on earth do I get a mechanism that explains this outcome? Where the alpha proton seems to get swapped, it's a substitution reaction, obviously, because the H is lost, and the Br ends up in there. How on earth does this work? Well, it's useful because those products can be used in all sorts of organometallic reactions. These things are very useful. They tend to be dangerous, these things, if you ever come across them. They make you cry. It's like the worst onion you ever saw. They're lacrimatory. They really make you cry, so you can tell whether these things are around. Well, to get there involves quite a complex mechanism, again, which I'll start now. And then Tricia is onto something over there in terms of selectivity, in terms of regioselectivity. If you start out with a system that is not symmetrical, that has 2 types of alpha proton, left and right, you can get 2 different products. And in this example, it's showing you the fact that you get mostly this, which is highly substituted, and you get less of this, which is the less substituted. And we'll have to understand that, see where it comes from. Now, I don't see anything here that's nucleophilic. I don't see anything there that's electrophilic. So I have a very hard time trying to wonder what's going on. And I'll tell you the fact is you run this at low temperature. What would happen with bromine if you heat it up? You get radicals. Now, radicals tend to be somewhat selective, but if you've got a whole bunch of hydrogens that can come off, you know, you get bromination all over the place. You only get this is the major product. This is pretty much it. So that tells you there's something else going on behind the scenes. It's not as simple as it looks. So what we have to understand now is that the nucleophilic species has to be the enol, because the enol has a pair of electrons at the alpha position as part of a pi bond. That's the answer. The enol is the nucleophilic thing. So to get to the enol is simply photomerism. So we'll start out with the ketone, as we have many times. We're going to protonate this thing, right? You're going to end up with a resonance stabilized carbocation. And that then loses a proton at the alpha position. This looks an awful lot like an E1 process. And there you are at the enol stage. Now, the enol is the nucleophile. You can't do that with a ketone because there's no lone pair there. But once you have an enol, you have a nucleophile. So this is proof, I think, that the enols are real and are in that flask. You can see at the bottom a mechanism that should not come as any surprise to anybody. A mechanism that we have done in little pieces many times. So this is very much like the addition of Br2 maybe to alkenes previously. We're maybe not going to draw bromonium ions here, but this is, because maybe we don't need to. We're going to attack the bromine. Bromine is polarized when you put it by a double bond, way back. We attack that, the other Br behaves as a leaving group, and we get formation of this. Now what would you draw if you were me? What would you draw next to this thing? A resonance structure, right? Because you might not use this arrow here, you might just use this to show it being a nucleophilic attack. And why has the bromine gone here and not here? What type of addition is it? It's Markovnikov addition. And if I do try to draw my resonance structure very carefully, that is missing from that slide, I would draw OH, IO, positive charge right there. That's the resonance structure for that molecule. So why do I want to put my positive charge there in a Markovnikov sense? Because I got some lone pairs to help out, which is this resonance structure down here. If you put the bromine on the carbonyl carbon, you don't get any help with the carbocation. So it makes sense. So that's a Markovnikov addition. M for Markovnikov. All you have to do then is deprotonate, and we're done.